Assalamualaikum and a good day to everyone. I hope you all are in a good conditions, especially during this pandemic COVID-19 virus. So today on 2021 I2CACIS International Conference on Automatic Control and Intelligent Systems, I will present my study regarding development of non-parametric model and speed tracking control of track vehicle electric motor, which is prepared by me, Muhammad Akimullah bin Subari, Associate Professor Dr. Hismullah Huda, Dr. Zulkifli bin Abdul Qadir, Associate Professor Dr. Syed Muhammad Fairuz bin Syed Muhammad Dardin, and lastly by Dr. Nur Hafizah binti Amir. Now, let us go to the introduction. Firstly, track vehicle can be defined as an extraordinary vehicle that have two sets of metal or rubber track on inner and outer vehicle instead of tire. So this track vehicle is commonly used or operates in difficult to reach situation and on a heavy road conditions. Now in track vehicles, it can be divided into several systems, which is for powertrain system, suspension systems. In context of powertrain systems, internal combustion engine, which is ICE, that use either diesel engine or gasoline engine, were introduced in early stage during development of track vehicles. Later on, in order to evaluate the emission of greenhouse gases, pure electric vehicles, which is EVs, and hybrid electric vehicle, HEVs, were introduced. Now, the difference between EV and HEV is EV it use only electric motor and battery to maneuver the vehicles. Meanwhile, for hybrid electric vehicle, it use both electric motor and ICE to minimize the emission and improve the time efficiency for vehicles during maneuvering. In this study, an electric motor for the usage of EVs and HEV in track vehicle is proposed. Next, we will go to the modeling of track vehicle electric motor. Here in this study, we are using non-parametric model. In non-parametric model, it can be divided into several types of transfer functions, which is either first order transfer function, second order transfer functions. In this study, we are using the second order transfer function, where the general equation is Gs equals to K omega n squared over S squared plus 2 epsilon omega n S plus omega n squared, where the value of K can be denoted as a DC gain, omega n is the natural frequency, and E is the damping ratio of the systems, where the subsystems of K, DC gain, natural frequency, and damping ratio were elaborated here. And then, in order to obtain the value of K omega n, E, the output and input EO and EI, we can use a characterization process, where here in the characterization, we are doing it in 20 seconds for the motor speed of 20 degree per second. As we can see that from the characterization results, we can obtain the value of the parameter that is needed for the track vehicle electric motor second order transfer function. Next, we will go to the speed tracking control of track vehicle electric motor. The setup is start by developing a real-time block diagram of track vehicle electric motor in MATLAB or Simulink software. As we can see in the figure, the block diagram represents a controller actuator for right and left motor. The desired angular speed is the initial speed setup, which is measured in the degree per second. Then the analog input is the reading of actual angular speed for right and left motor that is computed from Hall sensor built in from the motor. Meanwhile, the switch functioning in determine the direction of motor, whether we want the motor to rotate in clockwise direction or anti-clockwise direction. Next, we will go to the results. The results, as can be shown in the slide, is the speed tracking control on right motor and left motor with step input and sign input. Here is the result and discussion. The electric motor was tested at angular speed of 20 degrees per second on two types of input signals, namely step input and the sign input, as mentioned earlier. The results were validated between the non-parametric model, the track vehicle electric motor, and the desired input. Based on figure 1 and 2, the non-parametric model of track vehicle electric motor was able to follow the desired angular speed. The rise time recorded was 0.005 seconds on both electric motor and 4.3 seconds is required to achieve the steady state. Then, around 5.85% of overshoot were recorded during simulation on non-parametric model of electric motor. Meanwhile, the actual right and left electric motor were able to follow the desired input of angular frequency. The maximum percentage of overshoot recorded for both electric motors are 7.5% for right electric motor and 10% for left electric motor. Then, due to electric motor characterization of having a high torque, the rise time recorded was quite fast, which is at 0.8 seconds for both electric motor. For the response of sign input, as shown in figure 3 and 4 for 0.25 Hz, it can be seen that the electric motor was able to follow the desired angular velocity. This shows that despite of rapid transient response from 0 degree per second to the desired, which is 20 degree per second in just 2 seconds, only 0.5 seconds of delay were recorded. Lastly, the parameter of the PID controller for speed tracking control is tabulated below, where the parameters were obtained through knowledgeable tuning, where the parameter of Kp is 11, parameter of Ki is 0.1, and lastly the parameter of Kd is 3. It's all of that. Thank you.